Well, it looks like we can get started. Welcome back, everyone. It's probably the nicest day of the year already, so I appreciate folks deciding to spend time with statistics. That's tough to do sometimes. Any questions at all, folks, before we get started? Okay, well, our announcements are kind of over here, but just in case you dropped right in, let's run through them and see what's going on. We're nearly done with chapter 19. And if I somehow forget, because I used to just going chapter to chapter, don't hesitate to chime in. We need to do this document right after. And in some sense, this document is kind of a review for the final exam, where the major skill we need to apply there is choosing the right statistical method so that we can analyze the data appropriately. Before we get to chapter 20, we ought to take a look at that since we already have three big methods available to us. And understanding those differences really helps retention on how to choose the right method. And it's also going to be helpful for exam 3, since several of those methods here are exam 3 questions. Our exam 3, like we mentioned, is covering just these chapters right here, since we've had good time to cover them decently. And probably that means the best way to study for this exam is definitely get the homework done as soon as possible. Like I've done on other exams, this section right here is going to be due on the day of the exam, Wednesday. But if you decide to complete it early, my goal over the weekend and before Wednesday's class is to grade those as soon as they come in. So the moment you send those in, I might not grade it instantly, but that's going to be my next thing to work on over the weekend before Wednesday's class. That way you'll get good feedback on chapter 19. And that's far away superior to anything we could do on next Monday. But we'll still review on next Monday. That's still helpful, I'd say. So come prepared with exam questions you'd like to discuss, and I'll be happy to help out. Like before, if we spend all day reviewing, then I'll just assume that that was time well spent. If we kind of pitter out and run out of questions that folks want to ask or discuss, we may move into chapter 20 if it makes sense. I wouldn't go into that chapter if we have like 12 minutes left, but if we have enough time to make decent headway, we'd possibly do that. Oh, didn't mean to scroll. Other thing to definitely mention again is there was some confusion, some contention on the calculators during exam 1. It became irrelevant during exam 2 since that one was a take-home exam. But for the third exam, I felt like the calculator wasn't meant to be super restrictive. I said that this is required, but we're going to go against it. If you bring any scientific calculator that you're just used to working with, I'll be okay with that. Any questions or comments at all, folks, before we get started or about those announcements? Oh, sorry, I missed a chat down there. Olivia says, so sample exam 3 problems are for a grade, correct? No, these are more just for practice. This one is not an actual assignment. This will just be a way to get additional practice on those kinds of questions. So I encourage you to take a look at them. And definitely if you see a problem on there that you're not quite sure how it should go or something along those lines, ask about it during our review and I'll be very happy to go through it. Full disclosure though, we've done all these problems, almost. This is just the chapter 17, 18, 19 notes where I took out the actual formulas and things like that and sort of rewrote the questions so they look a little bit more like exam questions. So they're old problems, still kind of good to practice. But because of that, I'll also be including more problems just so we have some variety. I want to do that as soon as possible, but instead of saying I'll probably get it done on Friday or probably get it done on Saturday, I'll go with this as my final deadline. I want to for sure have that done before Monday's class. Probably early Monday would be the latest time I would get that in. That way you might have an opportunity to take a look at them and decide on questions you might want to ask. But other questions or comments so far? Okay, well, we're nearly done with chapter 19, our first chapter on analyzing categorical data. So let's jump back in there and see how all that's going so far. We mostly left off right here on this problem. This was the last problem we completed. The first thing that was going on here, just as a quick review on our Monday's class, was this was the central limit theorem from the very top of the notes, that the statistic p hat has sampling distribution, which is normal. The center of it, the mean of that statistic p hat, is the true population proportion p, and the standard deviation is this expression that we mentioned. This didn't happen in chapters 14, 17, 18, but it happens here in chapter 19, and something similar will happen in chapter 20. If you have a null hypothesis, this is only for hypothesis testing, not for the confidence interval procedure. But if that's your null hypothesis, the value here is irrelevant to anything between 0 and 1, then you assume that that null hypothesis is true, and that affects the value here and this one as well. From there, we know the true standard deviation for the statistic p hat, assuming the whole null hypothesis is the actual reality of the population. So from there, we're able to build an unusual looking test statistic. That denominator is not the standard error whatsoever. That's the true standard deviation when the null hypothesis is true. But the rest of the test statistic probably looks very familiar. For example, in chapter 17, the test statistic was t equals x bar. X bar is playing the role of p hat in this chapter's notes. X bar was the sample mean, and p hat is the sample proportion of successes. We subtracted mu naught coming from the null hypothesis, and then we divide by the standard error, which came out as S divided by the square root of the sample size. Only big difference is this one is actually a standard error, and this one is directly right out of the central limit theorem. It's not just that came out of the central limit theorem, so did this stuff. Right here, we want the expected number of successes, not in the sample, but the expected successes we would have believed to get when the null hypothesis is true, and the expected number of failures to both be greater than or equal to 10. That's inherited directly from the central limit theorem. If we scrolled up to the very top of the notes, that was the benchmark to assume we have reliability when we make this approximation right here for the sampling distribution of p hat. We want successes and failures to exceed 10. So hypothesis testing in this scenario is actually a pretty powerful method, only because of the distribution for p hat and the form the central limit theorem takes. So with all that knowledge armed, the p-values are exactly the way you did them in chapter 14. So this is essentially one huge review. When it says z is in the problem, that just means we're dealing with the standard normal distribution. And that's why you're using p-norm in this context. It's worth reminding because it's actually an easy mistake to make. I've done it myself, to go back to pt, because we're used to using that, the t distribution in chapter 17 and 18. But you always have to take a look at this kind of information here. It's directing us, if it says z, you're using the normal distribution once again. So aside from that, we left off right here. We did an analysis on this problem and just stated the practical question down below here. So now we're ready to run through this problem and see just what happens. Any questions or comments at all, though, with the quick rundown? Okay, well, these data look extremely serious. I don't know what a lot of these words even mean, but that's why this class is an important class, I would say. If I was being totally honest, I would say statistics isn't my funnest class. I like teaching classes like linear algebra, calculus. Those are pretty fun. But I would say this is the most important class I teach, statistical methods. Because these data, even if you never look at data like these, you're probably going to be confronted with data. Maybe it's a capstone project as an undergraduate, maybe going into graduate school. You'll find your own data that is very, very important to you. And so treating this with respect, giving it extremely careful analysis, this is all just preparation for the future when you have to do the same for your own problems. So again, I'm not too sure what's going on here, but let's work through it and just see what we can say. Reading it again, it says in the article that prothrombotic factors in children with stroke or porencephalopathy, they said that this author compared differences and similarities in children with arterial ischemic stroke and porencephaly. Probably pronouncing those wrong, but just doing the best I can on these. That looks like that's going to be the indicated population. It said down below, he had 3 classification categories for those children up here: perinatal stroke, delayed perinatal stroke, and childhood stroke. But then they went on to say, of the 59 children in the study, 25 were diagnosed with delayed perinatal stroke. And the question is about, do the data provide evidence to conclude that, once again, delayed perinatal stroke does not compromise 1/3 of the cases among the 3 categories? Kind of an interesting statement right there, but that's why we said delayed perinatal stroke is going to be the successes in this problem. It seems to be what the study is all about. And why would someone do an analysis like this? Well, maybe if you're, say, specialist pediatrician doctors at some point, you might have some expectations of what happens with these sort of children. But maybe in your practice, you're getting different kinds of data for one reason or another. You might start to suspect that maybe the established literature that this condition happens about a third of the time amongst the three is wrong. So you would do an analysis, test if we can find that evidence. And if you did find that evidence, that could really affect how these kinds of children are treated, the therapies and those kinds of things, or even more along the lines of your practice might be better equipped to handle these kinds of situations if you know that they come in at different rates, not 1/3. So that's possibly what this problem is all about. Or you could read the study in the Pediatrics Journal just to see just about everything about this problem if you're interested in it. Never ever have to do that in this class, but it's kind of cool whenever we have real data you could dig into. So what we did in this problem was we just restated the practical question. So here it is. We want to know if the data provides sufficient statistical evidence to conclude delayed perinatal stroke does not compromise 1/3 of the cases among the three categories. First thing we ought to do is define the parameter. This is absolutely categorical data, two outcomes. The moment we said there's 25 successes. So we'll say that P equals the true proportion of all, well, beyond all, we're essentially just mentioning the population, and the population is children with arterial ischemic stroke and poor encephaly. So let's write that down. This is a lot of writing. Apologies for that portion of the problem. P is the true proportion of all children with arterial ischemic stroke and porencephalopathy. Should definitely try to pronounce or spell that word correctly at least. So we mentioned the population. It's a proportion of these children that go to where the successes are and just say have delayed perinatal stroke. So that's our parameter. Once we have that down, we now need to set up our hypotheses. And looking through these data, there's one thing I neglected to write down. So let's do it right now. The question was asking, do we have statistical evidence to conclude delayed perinatal stroke does not comprise 1/3 of the cases? But right there, that's a value we need. It's kind of hidden there. That's a value we typically indicate as P naught. P naught is 1/3, and that's the status quo. It seems that the established literature for this condition says expect that this condition happens at a rate of 1/3. So that's our null hypothesis, a statement of no change. Nothing new is really happening with this segment of the population. We'll just say H naught. This population proportion equals the 1/3. So that sets up our null hypothesis. Next, we have an alternative hypothesis. And you really do copy most of what you said in your null right over. You still use the same parameter. You still use the same value to be tested, the P naught 1/3 that we indicated. But now we must decide on a test. Any volunteers for which test this should be? Left-tailed, two-tailed, or right-tailed? Oh, sorry, missing in the chats there. A couple folks, Olivia and Hannah, say two-tailed, and yep, that's exactly right. This one's a two-tailed test, and if you're not sure what the keyword was that indicated it, it was this right here. Does not compromise 1/3. When it says does not compromise, they're testing both directions. Maybe they suspect it's above 1/3 or below 1/3. They're really just not sure. So we're testing this way. So now that we have that down, one thing that's also worth mentioning here is if we're just totally not sure, maybe say you're doing something in an exam setting, this is always the default test, the two-tailed test there. So even if you got that wrong, you wouldn't miss too many points there. I'd say you need to find something that indicates that this is a less than or greater than, and if you can't find it, stick with the two-tailed test is great advice. Well, let's see what else we have. Did they give us a significance level? Answer this question by providing complete analysis using hypothesis test. That's why we have a null alternative at the 1% significance level. So from there, oh, we did indicate that. I'm just not caught up with what we wrote before. So let's just take that, drop it down here. Alpha equals 0.01. So that's all the preliminary analysis for these data. We've set the unknown parameter, which we're going to test, as well as our hypotheses. Next thing we do is check conditions. And this is absolutely tricky. I want to mention right away, if you're checking conditions, the first thought you should have is this a confidence interval or is this a hypothesis test? Because those conditions change. Let's scroll up just to indicate what could go down. Takes a minute to actually scroll up on this. So if we go to our confidence interval, we need to check that inside the actual sample, we have at least 15 successes and at least 15 failures. I almost said 10. Also check that the samples change for these. But this is directly in the sample. If we're doing a hypothesis test, then everything's been switched around, and that's word right here. The expected number of successes and failures when the null is true, that definitely deserves emphasis because it's all about that. So we'll take that, calculate those expected successes and failures by assuming this is true right away. So let's take a look at how this is going to go down. We need a sample size. And so the work for this would look about like this. When H naught is true, in other words, we just said the true proportion is exactly 1/3. The number of expected successes is n times, and the formula they typically give is P naught. That's how we stated it in the notes. The value for P naught is this right here. It's kind of up to your option though, because P is equal to P naught. So if you wrote it this way, that's just as good. But keeping in how the notes is written, I'll use the P naught value. So we'll take the sample size of 59, multiply by P naught, which is 1/3, and get a value out. If this dips below a sample size of 10, then we're not going to get an accurate p-value, and we need to use a different procedure to analyze the data. I think we should be good in this problem. 59/3 comes out as 19.6 repeating. For full credit on work, you do need to show this number so that I know that you know the actual expected number of successes. I usually put this in, greater than or equal to 10, as just a reminder for me. That's the benchmark that we had to hit. So we're all good on this end. Next, we write out the expected number of failures is, the way I usually calculate this is I just take 59, take away the 19.6 repeating, and it's that number there. So that's a decent strategy to take if you like. If you are a fan of formulas, let's put down the formula here as well from the notes. You could also calculate by taking n times 1 minus p naught, which is now n times. This is 1 minus 1/3, so 2/3. And I forgot to put an n, so let's just take another step there. N is 59 times 2/3. Let's just calculate it because it feels right to do that as the next step. 59 times 2/3 comes out as the 39.3 repeating. which also exceeds the benchmark of being at least 10, so greater than or equal to 10 there. After showing these two numbers, the 19.6, the 39.3, we can now safely assume, and so the sample size is large enough. So we're all good on that end. It's not the most critical condition. Probably the most critical condition that we really want to check is that we really have a representative sample. The gold standard is that we have a simple random sample, but anything they tell us about randomization is a comfort there to say that condition would be met. Rereading the problem, they didn't say anything about randomization, but let me double check just in case I missed something. Here's where the 59 children were first indicated in the problem, but they never said how they got those 59 children. So that's just a total unknown to us. It doesn't mean the condition fails. We can still analyze these data, but we ought to put down a disclaimer in our conclusion, if we recall, or just here at least, that we don't know if the conditions are fully met. It depends on randomization. Usually I put a statement that goes about like this: assuming the 59 children came from a random sample, the conditions are met. So again, it's an unknown to us, but this was a pretty serious study. They probably did have at least a representative sample, and we hope they also used randomization to get their data. So that is the condition checking process. It's sometimes a slog, but it's important work right there. Any questions at all, folks, on that portion? Okay, now we are to the fun part where we're just going to do a little bit of math, get a p-value out, and give a conclusion to our hypothesis test up here. We need all this stuff, so let's take a screenshot as well. I'm sure it's kind of disorienting if we're constantly scrolling up and down to reveal that stuff, so let's just put it down here. So when it says carry out the necessary computations, really you have to produce two things. We need a test statistic, and after that, we'll calculate a p-value. So first, the test statistic is z. Z is going to be calculated by taking p hat, subtract p naught, and we will divide by the true standard deviation of the statistic p hat, which is by formula square root p naught, 1 minus p naught, divide by the sample size n. So there's our formula. It's kind of clunky this time because of the situation with the hypothesis testing in this section, but we just have to deal with it. First thing to calculate is p hat. And one thing I recalled about p hat is the sample size was 59. I'm looking at it right up here. I'm kind of cheating. I don't recall the number of successes, so let's go and find that. Delayed perinatal stroke was a success, and there was 25 of them in this problem. So it's 25/59ths minus the value from the null hypothesis. When it says p naught by formula, the naught you can think of as h naught, and it's referring to this value right here, so minus 1/3. So already we have some interesting stuff in the numerator. There's a distance between the actual data right here in black and the value in the null hypothesis. We have that 25/59ths minus 1/3 is some positive quantity, but that quantity is truly irrelevant to us unless we put the standard deviation down there. What a test statistic tries to do is approximate the number of standard deviations that the statistic is away from the statement of the null hypothesis. And this time it's a really good approximation because, well, that is the exact standard deviation, assuming the null hypothesis is true. So let's now put in the rest of this stuff. It'll be square root of p naught once again, which is 1/3, multiplied by 1 minus 1/3, could just put 2/3 there if you'd like. I'll write out this way, just so there's a paper trail in the notes. Then divide by the sample size, which is 59 once again. So now we need to jam all of this into the calculator. I've said this a lot, but it's always a good reminder since it's sometimes a lot of partial credit. If you're doing exam 3 and you write out stuff like this, that is humongous protection to any mistake you could make putting it in the calculator. So let's try to get it in right. We need a parenthesis for the numerator. Oh, let me get back here. There we go. So there's the numerator, 25/59 minus 1/3. Now another parenthesis, or we don't need a parenthesis. We need the square root for the denominator. So SQRT in this calculator. Now up above, I'll just pretty much put it in verbatim, but as a line, it'll be 1/3 times, I'll just simplify this one to 2/3, then divide by 59. An order of operations is kind of nice. You can just go left to right, top to bottom, and this will qualify for correct order of operations. Oh, I need one more parenthesis. And I needed something else. Let's see. Unexpected closed delimiter in 25/59 minus 1/3. Somewhere in there, I have a messed up delimiter. Let's see. Probably in the square root. I have 1, 2, 3 open parentheses. That means I should be closing 3 parentheses in total, but let's see if that works out. Oh no, it's not working out. I don't see where it could have gone wrong. It was all going so well into this point. Sometimes when I make a mistake in RStudio, this is literally what I do. Let me know if you find the mistake, but because I made the mistake, it's invisible to me now. You're probably better at finding it than I am. I'm just going to try to retype it and hope I skip over that mistake. 25/59 minus 1/3. Divide by square root 1/3 times 2/3 divided by 59. And that time it worked without a problem. There's something messed up with those parentheses, but we don't have to reverse engineer that. Let's just take this correct value, 1.4729. Oh, and we've got some chats coming in. At the very end, yeah, it looks like I just put in some weird parentheses. Thanks for mentioning that. And as I'm looking at it, I'm still not completely certain where it went wrong. I have parentheses there to there, there to there. And oh yeah, it's just that additional one. And then I try to fix it by putting in even more parentheses. That's not a hack that works well with RStudio, it looks like. Thanks for taking a look at it though. So how's that look to folks? Are we all getting about 1.4729? Excellent. So this now tells us that the sample data right here, where p hat is about 1.5 standard deviations away from the assumed value of the population proportion. That's quite a lot of standard deviations, but we're going for a 1% level of significance. Doesn't look like we're going to actually reject the null hypothesis on this one. But we can't go with doesn't look like. We need to really assert that by calculating a p-value. That's our next step. In doing that, we have to recall we're doing a two-tailed test because of the not equals. So for the two-tailed test, we calculate the p-value in this way. The p-value is going to be equal to, from this portion right here, the fact that we have a two-tailed test, we have to double p-norm. We got a positive value, so I'm going to accumulate area to the right of 1.4729. So we need to set lower dot tail equals false. If that was negative, I would just drop the negative value here, close the parenthesis, and then you'd be done. That's kind of confusing. So also, if you're not sure what should go here, that's what the purpose of this portion of the document is. Just a one-stop shop for how to get the p-values out. So now that we've got this set up, it'll be p-norm of this quantity, 1.4729. So we place z right here. There are no degrees of freedom for this problem, so immediately go to lower dot tail. Set false. So now we're just about have it. Back to RStudio, let's see if this syntax works for us. 2 times p norm 1.4729 lower dot tail set false. And we get a p-value of 0.1408. And again, that's a pretty large p-value. What it's telling us altogether now is the sample data right here is consistent with the statement of the null hypothesis because it wasn't very many standard deviations away. And the probability of getting data as extreme as this data, or even more extreme, when the null hypothesis is true, is about a 14% chance. That could happen quite often, so it looks like this is typical looking data. It's not rare like we're expecting it to be. So we're about ready to give a conclusion. To orient ourselves, you might also add here that this is greater than or equal to 0.01, which is equal to alpha. And so in this problem, we will fail to reject H naught. So we're about ready, folks. All we now need is an overall conclusion. We can say something along these lines. The sample data does not provide significant statistical evidence that this is true right here. It's a heck of a statement we have to write out. But one thing that I do try to do when we grade these things, and I think I've mentioned it a couple times, we have to be pretty careful when we write down the parameter the first time. We have to indicate what population we're working with, what the successes are for this type of parameter. But when you go to write down your conclusion, if you decide to paraphrase this a little bit, I would say that's appropriate. And this is the part I'm going to paraphrase. Instead of writing out that statement once again, we can just say that the true proportion of these children, so that's the paraphrase I would take. And I'd say that's an appropriate thing to say at the conclusion because we've been studying these grouping of children all along. We indicated in a parameter. So referring to these children is still well within context after you've defined that parameter carefully. So I'll just say these children for that yellow portion, the true proportion of these children that have delayed perinatal stroke is different from one-third. So the study was not able to provide that significant statistical evidence. It does not mean that this is true at all. But what it means is if we couldn't find the data to reject this, maybe the true proportion is, aside from one-third, maybe the true proportion is, say, 0.33 or 0.34, something like that. That's a true difference, but the difference is extremely small. Potentially, it's going to depend on the expert's analysis of how small that is. So that even though there was no significant difference we found, we might have also decided that there's no practical difference between this value, if it's the true value, and the value to be tested of one-third. So there's a lot going on in this problem, but that's safe to say now, if you were a doctor that looks into these kinds of issues, you can start to treat your patients as this being a consistent statement. Not that it's true, but if we didn't find any evidence against it, it probably wasn't terribly false. We couldn't detect it with our sample size. Well, that's the final conclusion of this problem so far, folks. Any last questions on handling the hypothesis test with these type of data? Okay, I like to mention once again that when you're looking into the conditions, chapters 19, 20, 21, 22, and so on, they're all very tricky. It depends on the method you use. Confidence interval conditions and a hypothesis test conditions go totally different. But if you're analyzing quantitative data, maybe it's one mean in chapter 17, two means in chapter 18, the conditions you check, whether it's a hypothesis test or a confidence interval, it's all the same thing. So that's kind of nice in that setting. Well, we're about ready for chapter 20, but before we go there, let's do the thing that we promised. Let's start looking at different groups of data and see how we can tell exactly why one method would be picked over the other methods that we have so far. Once this document stops trying to save, there it goes. So where I'm going to next is this right here. Opening it up as a PDF, I wrote here to start that it's an evolving document that will be updated over time. That means it's going to move around. Every time we go to a new chapter, I'll put this right down below. I'll probably add more and more problems over time. And we'll not necessarily try to complete all of it, but we'll work on this document over time as well. It's not necessarily the actual review for the final exam, but it's just extra practice to help us get there. So let me open the Word document we can edit. So all these problems ask us to describe the variables of the study. And that's returning right back to chapter 1, the very first day of class, back when it was January. Once we find what the variables are, we'll base our information here for what statistical method to use on the form of the variables. And that's pretty much what we're doing from problem to problem, trying to tell apart the methods. We'll probably end right here on problem number 5 and leave problem number 6 for after we complete chapter 20. So let's go down the line. This is a first problem. I'm not sure if we've done this problem or not, but it says dementia is the loss of intellectual and social abilities severe enough to interfere with judgment, behavior, and daily functioning. They tell us next, oh, that was weird. Let me see if I can fix that. Alzheimer's is the most common form of dementia. So in the article, Living with Early Onset Dementia, really long article from the Alzheimer's Care Quarterly, P. Harris, J. Keaty explore the experiences and struggles of people diagnosed with dementia and their families. So this is pretty serious data as well. They tell us next, a simple random sample of 21 people with early onset of dementia gave the following data on age at diagnosis in years. So this is pretty rough data again. I mean, this person right here is my age, and getting a diagnosis like that is a very devastating thing. So that's serious data we're looking at again. But if you were to describe the variables of the study, what would you say the variable ought to be? I think I kind of just gave it away. Sorry, I highlighted this and then I asked the question about that. That was my bad. I'll take this question. The variable on this would be age at diagnosis. So that's our variable. When it says to describe it, we also want to say whether it's quantitative or categorical. But if we're looking at numerical data like this, it's just absolutely quantitative data. So we'll say here, this is quantitative. So you probably already know the right method. If you have one quantitative variable, this is something you would use in chapter 17. Let's say down here, for exactly one, quantitative variable, use the one sample, T methods of chapter 17. And the way this problem is written is the way some of your final exam questions would be written. It says perform a complete analysis. So what that means is you get to pick the analysis. You might do a confidence interval, you might do a hypothesis test, whichever makes more sense in this problem. Looking at the form of the question, that looks like it's being asked as a hypothesis test right here. Looks like a left tail test because it said less than, But you could still analyze this as a confidence interval if you choose to. So it's kind of be up to you on these kinds of problems. But this is why we would use the one sample t procedures. So you would just go to, if this was a real final exam question, analyze the variable, decide which methods you have to use. And then the Moodle website is now effectively just a long document where you can go folder to folder. You could grab something like the one sample t procedures. If this is not enough help, you can look into the fully fleshed out examples to see how it all goes. And that's pretty much going to be the experience of the final exam. But this is a good point of the course to right now start thinking about this. Which method should we use based off the data? Well, the first one wasn't too bad. Any questions at all, folks, with problem number one? Okay, let's keep on going. I should mention, by the way, if any of these problems look really interesting, be sure to mention that on Monday's class. We can turn any one of these into a review question. Maybe not one that is beyond exam 3, that might not be appropriate, but I'd be happy to for the ones for chapter 17, 18, and 19. So moving down the line, this kind of question is always extremely confusing. We made kind of a big deal out of it in chapters 17 and 18 when this type of things came up. And it's also historically one of the nastier questions on a real final exam, so that's why I always make a big deal out of these data. Let's read through the context to get a feel for what's going on. They say, biologists studying the healing of skin wounds measured the rate at which new cells closed a razor cut made in the skin of an anesthetized newt. So they grabbed anesthetized newts and they made a cut with an X-Acto knife or something along those lines. So maybe put a page break here. In one experiment, the 2 hind limbs of 14 newts were assigned at random to either experiment or control groups. So each newt had 2 hind limbs, and either the left limb got the experimental treatment or the left limb got the control group, and they randomized which was which to kind of eliminate any weird factors on healing rates potentially. And what did they do? They said the electrical field in the experimental limbs was reduced to half its natural value by applying a voltage. So they cut them and electrocuted them after anesthetizing them, but kind of feel bad for these newts. The control limbs were not manipulated, and the data in the table below gives the rates in micrometers per hour at which the new cells close a razor cut in each limb. So both hind limbs had a little incision. One of the hind limbs had a voltage applied, and they're saying, would that impact the healing rate? So it just sounds like a mad experiment, to be completely honest, but this is real data. They ask us, is this good evidence that changing the electrical field from its natural levels slows healing? That looks like a left tail test as a hypothesis test question, or you can decide to use a confidence interval to analyze it. First thing we want to do is describe the variables, but this one's tricky. Any volunteers for the explanation of what makes these 2 variables here tricky to analyze? Exactly. We're looking at paired data. So if every one of these values, say the 46 and 42, came from the same individual, the same newt, well, these are dependent data altogether. So when it said describe the variables of the study, this is almost a trick question in a certain sense. You wouldn't describe this one. This is the identifier, but you don't necessarily want to describe this one nor this one either, because the actual variable you're going to analyze for this type of data is the differences between the 2. So let's mention this right here. From this right here, we know that these are paired data. And we've solved this as a chapter 17 problem as well. Whenever we have paired data where individuals are used multiple times, the data is dependent and we will form the differences. We will analyze the differences. So again, we could describe experimental limb and control limb, but what we should really describe in this problem is difference in healing rate You can subtract either way you'd like. You could take experimental minus control or control minus experimental. They ask the question, is there good evidence that change in electrical field from its natural level slows healing? So it seemed to indicate that this probably has a smaller sample average. That means the analysis won't involve as many negative values if you went to control minus experimental. But again, as long as you're consistent in how you subtract, it really is irrelevant. I personally would probably go this route. Control minus experimental. So that's our variable. It's quantitative. And so now, the moment we have exactly one quantitative variable, because we're analyzing the differences, we revert back to chapter 17 once again. So let's just put out a quick statement. There is exactly one quantitative variable so we will use the one sample we call these the T methods or the T procedures because it reminds us we're using the T distributions to get critical numbers or p-values. I'll call this T methods. From chapter 17. So that's how to analyze these data. And what makes it really confusing analyzing these data is chapter 18 data looks almost the same as these, but we have to understand whether or not the data are independent or dependent. Paired data like these are always dependent. And now moving to the next question, these would be independent data, but let me not jump the gun too much. Any questions at all, folks, on this problem here before we move on to the next? Okay, well, let's take a look at the next question then. Problem 3 says, research has shown that people are more likely to show dishonest and self-interested behaviors in darkness than in well-lit environments. So already this looks like a psychology, maybe sociology type of problem. These are always really, really interesting. They say next, in one experiment, participants were given a set of 20 puzzles and they got 50 cents each for each one of the solved puzzles in a 5-minute period. So imagine being given like 20 random math questions, but being told you're going to get paid out on them, but you have to do them fast. It just doesn't sound like a wonderful situation. So they took all the participants and put them in an intentionally stressful, overwhelming situation. They go on to say, however, the participants reported that their own, let me try again. The participants reported their own performance. So now this is definitely sounding like psychology. So you're in a stressful, overwhelming situation. You immediately feel that this is unfair, but you get to decide which questions or puzzles you correctly solve all on your own. There was no obvious method for checking honesty, so that's really, really interesting as well. Thus, the test provided a clear opportunity to cheat and receive undeserved money. And I mean, if you're put in a really unfair situation, that's just a natural human response, in my opinion, at least. I haven't taken a whole lot of psychology. It goes on to say, one group of participants was tested in a room with dimmed lighting. That's the dimly lit room. Second group was tested in a well-lit room where you probably feel more exposed. And even though no one's checking you, the fact that everything's well lit just feels different. And the reported, remember, this is self-reported, number of solved puzzles was recorded for each individual. So taking a look at the data, just glancing at it, in the well-lit room, it looks like we have people behaving pretty honestly, yet somehow in the dimly lit room, these folks are just really good at solving puzzles, or maybe their behavior really changed based on the environment. But that was the only thing that they tried to change. This category right here, going from well-lit to dimly lit. That we want to know, is there significant statistical evidence of a difference in performance between these two lighting conditions? Very similar kind of questions with the newts and the healing rates between the control and experimental room. But this is a very, very different situation. It looks like they have, I don't know how many, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 students here, 9 other students here. but they're not necessarily the same student. If they were, we would have to emphasize this to properly display the data by putting something like this, like student number or something along those lines, maybe the student name, something like that. So now we have two independent sets of data, and we must describe the variables once again. Now, describing the variables is kind of tricky because this is the quantitative data right here. When you look at that data, you have to recall, what does this refer to? It's the reported number of solved puzzles for each individual. That's one variable. All of these data right here corresponds to the highlighting above. So I wouldn't necessarily say I have one quantitative variable here, another quantitative variable here, although that approach could work. That's not a terrible way to go. I think it's better to analyze it this way. Let's first say lighting. That's one of our variables in this problem. And this one is absolutely a categorical variable. This is categorical. When you're in chapter 1, whenever we set a variable as categorical, we also want to indicate the subcategories or the outcomes of the variable. So let's do that here as well. The outcomes are well lit and dimly lit. So the purpose of this categorical variable is to take all 20 students and just categorize them as to which experimental situation they were placed in, the well lit or the dimly lit. So we have exactly two outcomes. And that part's important. If there was three outcomes, maybe an intermediately lit room. So we have well lit, somewhat well lit, and then a dim room. There was three categories. That'd be an interesting experiment as well, but we can't use our typical methods. With three categories, it becomes analysis of variance out of nowhere. So understanding the variables and the nature, not just categorical, but the number of outcomes is also extremely relevant for these data. The other variable here was correctly solved puzzles. Let's just say number of self-reported correctly solved puzzles. I'll just abbreviate to solved puzzles. This variable is quantitative. And so now if we ever see this situation, if we have a categorical variable, this could be analysis of variance, a totally different procedure. But if you see this situation with one quantitative variable, then the statistical method we will use is the following. We must use the two sample T methods of chapter 18. Again, it's only because of that right there that this is allowed to work for us. Any questions at all, folks, with looking at this data and how to work on this one? Okay, kind of a fun problem. I'm not really sure how this one goes. I don't think I've actually done this problem. I just sort of grabbed it and typed it up for us. So if you're getting curious about any of these, we could make this a review problem. This is definitely a chapter 18 method. So a lot of times you see a table that just looks like this, you're probably dealing with the chapter 18 method of the two sample T procedures. But we have to be really careful with how the data is presented because it's not always immediately clear. So beyond that, if you do know the variables, that's what's always crystal clear. This is the exact situation where we use that method. Well, going down to the next ones. Here's where the reading gets a little bit tougher, and you can almost tell right away, we're moving from quantitative data with a categorical variable to looks like just categorical here. Not necessarily, you could have a problem that gives you summary data, but I also see a lot of percentages, and that's not a guarantee, but it's a red flag. You're probably dealing with categorical data. It goes on to say, let's see, I forgot what this problem was. the Substance Abuse and Mental Health Services Administration, sounds serious already, conducts surveys on drug use by type of drug and age group. The results are published in the National Household Survey of Drug Abuse, so you could check that out today if you want to look at some interesting problems. And according to that publication, 13.6% of 18 to 25-year-olds were current users of marijuana or hashish in the year 2000. So that's kind of interesting. That's what they say so far. And they go on to say, a recent poll of 1,283 randomly selected 18 to 25-year-olds, I think that's a typo over there, revealed that 205 currently use marijuana or hashish. So at the 5% significance level, does the data provide sufficient evidence to conclude that the percentage of that age range who currently use marijuana or hashish has changed from the year 2000 percentage value of 13.6%? So looks like that's the whole problem there. And I think this one's kind of tricky to look at, but taking a look at the data again, there's where the sample is, the 1,283 randomly selected 18 to 25-year-olds. They said 205 of them currently use marijuana or hashish. So that means that's one category. That sounds like successes. That's what the study is all about. The other category would be those, I guess you could say, young adults that did not use, let's just say THC. It's a little bit faster. So if that's the case, if you notice that this is the successes, then it looks like we're in a chapter 19 situation. But we need to be extremely careful about that because the problem down below right here also has successes, and this one is absolutely not chapter 19. So let's investigate this a little bit further. Let's first describe the variable, and let's just call it, again, paraphrasing, THC use. This is now categorical. We're just taking these individuals here and saying we have a success if they currently use THC and a failure if they don't. So that's categorical. And this part is the most important part, I'd say. Well, that's all important, but a very important part. Exactly 2 outcomes. They were current THC users and non-THC users. And this one was the success. Not that we're trying to promote THC use amongst the young adults, but that's what we were interested in, so we call it a success. So right here, you have exactly 2 outcomes. And another thing additionally, since there is exactly 1 categorical variable with exactly 2 outcomes, we will use the 1 sample. We call these the Z procedures because that reminds us this is now based on the normal distribution. I'll call this Z methods, only because the course is called statistical methods, so it just sort of makes sense. Of chapter 19, the chapter we just concluded. So again, this part right here, the fact that there's just 1 variable and it's categorical, but additionally, that 1 categorical variable had exactly 2 outcomes, successes and failures. That's what puts us down to the chapter 19 methods, the ones that we just concluded on. If we use a hypothesis test, we have 1 set of conditions to take a look at. But for a confidence interval, totally different set of conditions. That's to me, the most confusing thing about chapter 19. Well, any questions at all, folks, with getting through these this problem here? Okay, now going down on the document, this is where it gets a little bit tougher. These are the methods we haven't seen, but we'll be getting to. First, let me take a look at this. Let's take a look at this one together. This one is one categorical variable, but there's now three outcomes on these data. Here we have to use the chi-squared procedures. So we'll come back to this document when we're getting closer to chapter 21. Now these data, my claim it's not chapter 19, it's really a chapter 20 problem. Reading through it, it's not immediately clear. So let's break this up and see just what's going on here. To start off, it says the article, aspirin use and survival after diagnosis of colorectal cancer, so really serious problem again, reported that out of 549 study participants who regularly use aspirin after being diagnosed with colorectal cancer, we had 81 colorectal cancer specific deaths. This looks like a long-term latitude study where they were following people at one point of diagnosis with colorectal cancer, and then for many years until either they died naturally of old age or died due to their condition. Whereas among the 730 similarly diagnosed individuals who did not subsequently use aspirin, there was 141 colorectal cancer specific deaths. Now, the magnitude of the number is not as surprising as it looks because notice the sample sizes change from one to the other. So we'd have to look at the statistic to get a good feel for that. The question was asking if the data suggests that regular use of aspirin after diagnosis decreases, so it looks like left tail test, it just the incident rate of colorectal cancer specific deaths. So there's a lot of information inside there. And there are two variables. Any volunteers for one variable or the other? Just kind of like a blob of text. It's actually kind of hard to spot. That's what makes chapter 20 a little bit tricky, in my opinion. Let's maybe start off with this right here. Notice they mentioned 81 colorectal cancer specific deaths, and then they mentioned again 141 colorectal cancer specific deaths. See if I can highlight that. There we go. So that looks like successes and failures all of a sudden. A success would be dying to that cancer. So that's kind of morbid, but that's what the study is all about. So we might say that one variable is colorectal cancer specific death. Geez, that's a heck of a variable. We would definitely call this categorical since we're just taking all of the participants, the 549 here, the 730 there, and just categorizing them. Did you pass away due to your condition or to other causes? So this would have exactly two outcomes: success. Again, I always kind of feel bad for saying this, but the success would be person died. To the condition. And a failure, the person did not die to the condition. Okay, so that's one variable down. And sorry, it looks like I missed it, some chats. A good call, Aspen and Hannah. The other variable was whether they used aspirin or not. So that's the second variable there. Good eye spotting that. I think that's what makes chapter 20, in my opinion, really hard. It might be easier to find this part of the problem because it seems to be what the question's all about. But there was something else. If you can notice that there it was a split between samples. It looks like there's two independent populations, and that's the same variable that you're mentioning. So let's see if we can highlight it as well. 549 study participants had regular aspirin use, And 730 similarly diagnosed individuals did not use aspirin. And so our next variable is aspirin use. So again, this one is, oh, I forgot to say up here. Let me include this. For electrocancel specific deaths is categorical. Forgot to put that down. Let's put down here. Aspirin use is also categorical. We wouldn't call this one successes or failures, even though there's exactly two outcomes. We would just indicate the two different things that we're studying here. So categorical will say the outcomes are aspirin use or no aspirin use. After diagnosis. So we have two variables. Both variables have exactly two outcomes. Let's indicate here. Exactly two outcomes. And there's actually two different kinds of analyses we could get for these types of data. We could use the chi-squared procedure for two-way tables alpha in chapter 22, but that's not necessarily the best kind of analysis to give. There's a simpler analysis we can give in chapter 20. Chapter 20 will handle this situation. And in chapter 20, the two sample Z test for proportions, let's say not test, sorry about that. Let's say Z methods, because you might use a confidence interval method or a hypothesis test type method. So just call them all Z methods. So in chapter 20, the two sample T methods for proportions can be used. There's an exclamation mark because that's exactly where we're going on the next set of problems after the review, after the exam as well. But any questions at all, folks, with what we've got so far? Okay, so the purpose of this document is it helps us to identify what statistical method to use. And so if you're using, say, or if you're doing a problem like, say, the take-home final exam, and you're just not sure what method to use, we'll have another review for that, but you could also come back here to get some other motivation. Now we're nearly out of time, but let's take a quick look at that chapter. And take a look at it side by side with chapter 18. I want to give us a feel for after the exam that we're about to do next Wednesday, what we're going to be doing in chapter 20. So chapter 20, it's going to start off in this kind of way, which might give you a sense of deja vu in a way. There we go. Let's see. Oh, that's kind of hard to look at. Let me see what I can do here. So first thing we're going to do in chapter 20 is reuse this theorem that we did right above here. The whole purpose of this is we need to develop a theorem that goes like this. There'll be a brand new central limit theorem for the difference in statistics. So that's what we're trying to produce right down here. And the major reason we want to do that kind of work is we're just trying to connect the dots. Back when we were in chapter 18, that's a pretty weird looking standard error, but it really helps to memorize it if you know where it came from. And we have the same situation in chapter 20. The methods just get kind of ugly after a while. And that's our next standard error we have to produce to do a confidence interval. And it'll be something different if we're doing a hypothesis test. In hypothesis testing, we pull the proportions into what's now a brand new statistic. And we have a whole totally different standard error. This one's a real standard error. It's not an exact standard deviation like in chapter 19. So that's what we're going to be developing. So to see how to handle these data right here. It's important data, so we'll be able to give an honest analysis once we run through this portion right here, we just need a brand new central limit theorem. Well, I think this is a good stopping point. I don't think we can make any meaningful work in this direction in 4 minutes. Any last questions, folks, before we call it a night? Okay, well, have a great weekend, everyone. If you're working on the homework questions over the weekend, don't hesitate to email me. I'll be very happy to help out. Otherwise, I'll see you all next Monday on the review. Have a great one. Not quite yet. Thanks for mentioning that, Olivia. I'm going to be producing that exam 3. I nearly have it written. I'll send it off on Thursday morning. And after I've done that, I'll email you to let you know that you're able to schedule the test in Pocatello. And same for folks that are scheduling in the Idaho Falls Testing Center as well. So not quite there yet, but I'll be emailing you tomorrow morning or maybe around the afternoon, hopefully sooner than later. You betcha. Thanks for asking about that. Thanks to you as well, Aspen.